right, next up we're going to hear about TorchQL, and Aaditya is giving the talk.
Thank you. Hi everyone, I'm Aaditya. I'll be talking about TorchQL, which is a programming framework for integrating constraints in machine learning. So as we all know, machine learning models make a ton of mistakes, and they can range from things that are a bit more critical, like in this case where a person is not being detected by an autonomous vehicle, to things a bit more benign like bias in GPT 3.5, few mislabeled training data, and imputation errors in medical data. And in every case, finding those errors, those specific errors that we are looking for, is kind of tricky. To do so scalably, people typically go to performance metrics like accuracy, or use statistical techniques like outlier analysis or error rate analysis. But a problem with all these techniques is that they aggregate errors and don't really give you fine-grained feedback. So if you want a really specific error, you have to filter through a lot of potential errors to actually get the specific kinds of errors that you want. So case in point, I don't know if this is really visible, but over there you see 3 frames in a video, and there is a person in all 3 frames, except the person is detected in the first 2 frames by an object detection model and is not detected in the last frame. These predictions are given by a model called OneFormer, which has a pretty high accuracy on the Cityscapes dataset, which is for autonomous driving. And even then, it's unable to actually predict the person in the third case. And this is a very critical error, but it's also a very sparse error because it only occurs around 627 times out of 15,000 frames. So imagine filtering through all those frames just to find these kinds of errors. So we then looked back at this and we realized that this is a pretty basic property of object permanence that is being violated by this model. And we kind of extrapolate that to arrive at the core insight of our paper, which is erroneous model predictions can be cast as violations of integrity constraints. So we can specify integrity constraints over the outputs of models, and looking at their violations can give us specific kinds of errors that we want to get. So now that we have that, let's see how we can specify integrity constraints. So we will need a framework in order to perform this specification. And that framework needs to support a variety of features. So for instance, the framework needs to have a flexible schema because we are dealing with Python, and Python has objects of various kinds, not just numbers and strings that most database frameworks are used to. We need to support user-defined functions because constraints like object permanence are quite complicated to define. So you need to allow for the specification of those kinds of constraints. And you need to have querying abstractions because you want people to focus on actually specifying the constraints rather than writing how those constraints will be evaluated over the model. And that's what querying abstractions helps with. And then we looked at a few different frameworks. So we looked at Pandas, MongoDB, and Python. And in pretty much every one of these cases, there is some issue. So Pandas does not have a flexible schema. It only supports numbers and strings. MongoDB does not let you define user-defined functions. And Python, you need to basically implement the entire thing in Python from scratch. And so we proposed TorchQL, which is a querying framework that is integrated into PyTorch that lets you write queries as modules within your machine learning pipeline that you can just plug in and evaluate models over. So the setup is kind of like this. You have a user who can instantiate a TorchQL database and supply data to that database. This data can have objects of any kind. Over here, it's images. And in code, it looks something like this. You instantiate a variable called db, which is a TorchQL database, and you register the dataset in that database. The dataset string is denoting the name of that particular table, and it can be used for defining subsequent queries. Then the user writes TorchQL queries that are given to the database. Over here, our TorchQL query is going to try to get the predictions of the models. So we are looking again at the one-former model. And once we instantiate the model, we can start defining the query. The query is defined as having a name called preds, and it is based off the dataset table. And what we do then is we use a projection operator that operates over every single row of the dataset table and applies a function on every single row. Over here, our function is the model itself. We supply b equals 128 as a way of saying that we want a batch size of 128, so we have batched evaluations. It helps with scalability. And then once we have this query, we can run the query and give the results back to the user and also store them back in the TorchQL database for the user to write more queries on. And that looks something like this. Now that we have these predictions, let's look at how we specify object permanence. So I'm going to take you through my thought process on how I started specifying object permanence using TorchQL. And I started off with the simplest query possible. I looked at all the frames where at least one pedestrian is predicted, just as a starting off point. So in TorchQL, that looks something like this. We have a query named people count, which is based on the predictions. And we simply apply a filter operation over that, where you count the number of people in every single frame, in every single prediction. Now, count people, as you can see, is a function that has been defined somewhere else. And it can be arbitrarily complex, but for this case, it's literally a few lines of code that just takes all the people predicted and counts the number which are actually people. On the right, you can see the Python version of this query, and you can already see that it has some added infrastructure that makes it a bit more complicated. It's not a big deal right here, because the query itself is kind of simple. But as we go to more complex queries, we'll actually see the difference. Now, this is a very simple query, and it gives us a lot of false positives. So we move on to a slightly more complex query, which is finding all the cases where the number of people predicted changes from frame 1 to frame 2, where these two frames are consecutive. So what we do is we again look at the base prediction table, and we perform a self-join. But we perform a self-join over the condition that the predictions from the second column will be of a frame after the predictions from the first column with a time interval of 1 second. So that is FID plus 1 and FID. And then we extend the filter operation from the previous query to now filter for a difference in the number of people as opposed to just filter for the absence of people. The Python version, again, requires a bit more infrastructure in order to implement this. And over here, you need to start nesting for loops and adding more if conditions to actually express that. And then finally, we arrive at the actual object permanence query. Now, this is obviously a bit more complicated, but you can see in the first 3 lines of the TorchQL code, here's a 3-way join, because we're looking at 3 consecutive frames. And we then perform a few projections to track objects across those 3 frames, and then we perform a filter that removes the cases where there's no prediction in the last frame. And now here you can see the difference between the TorchQL code and the Python code. The Python code is way more complex to actually write and even read for anyone else coming in and trying to see what this integrity constraint is. And so we see that TorchQL provides these primitives and makes it easy. And in total, we have 8 primitives or operations that lets us write. In the process of making TorchQL, we wrote hundreds of queries. So these 8 encompass a pretty good set of primitives. Another example is, so using these primitives, we were also able to extend the functionality of TorchQL to actually apply to constraint generation. So what we do over here is we see that there are several times when LLMs will generate outputs that are incorrect or that are easily, like, I asked for a number, but I got some text instead, and I don't want that. And this is basically constraint generation for LLMs. On the left, we've written the TorchQL query that achieves constraint generation. But I'll explain the diagram on the right. So on the right, you can see that there is a function called genk that is responsible for generating the outputs of an LLM. What this does, it takes a chain of thought prompt, it takes a data set, it takes an LLM, and it produces answers for every single entry in the data set. Then it gets passed on to a constraint. As you see over here, the constraint is a lambda function. So this constraint can be literally anything. So you can even imagine a code generation LLM being constrained by the constraint that the output needs to be syntactically correct or adhere to certain static checks or things like that. And then it looks at the constraint and then it outputs the answer which actually obeys the constraint. And we compare this chain of thought to our standard chain of thought on the top and to LMQL chain of thought, which is another constraint generation technique, but that works token by token. And we see that TorchQL chain of thought is faster than LMQL chain of thought because we are able to scale much better. And it's also more accurate and produces more valid results than LMQL chain of thought. But it's still slower than your traditional chain of thought prompting because we have the added overhead of providing the constraints. And so we look at other uses of integrity constraints as well, and they include label correction, outlier detection, bias discovery, and in general, we implement all of these queries, but for evaluation, we consider 11 of those over 5 different tasks. And here are some numbers as to like the number of operators in every single query, but it's kind of a lot of detail. But essentially what we do is we write the same query in every single framework that you see on the top over there. So we write the same query in Pandas wherever it is possible, in ArangoDB, which is an in-memory version of MongoDB, in NumPy, that is only possible for 3 of these queries, and in Python. In every single case, we write it in a way we expect reasonable programmers to write in that particular language. And specifically in Python, we optimize the Python code as, to the level that TorchQL is optimized. And this is important. So we see over here that TorchQL always runs slightly slower than Python and NumPy, which makes sense because TorchQL is a Pythonic framework. And the overhead that is provided by the abstractions is negligible, sorry. But TorchQL runs much faster than ArangoDB and Pandas that are actual query processing frameworks. Now, the reason this is, the optimizations in Python were important was because in the cases of joins specifically, unless you optimize the Python code, your Python code runs much slower than TorchQL. So SQ1 took around 10 minutes and actually timed out over here if we did not optimize the Python code. But we brought, but to make things fair, we optimized it and brought that down to around 43 seconds over here. We also look at conciseness, which is just a way to approximate how much easier TorchQL queries are to write. For that, we just look at the number of tokens we needed to write the queries in every single system, and usually TorchQL requires the least amount of tokens to write them. We also conduct a user study where we give the users 3 tasks. Task 1 is like the simplest task and was basically achieved by the users in around an average of 4 minutes. And task 3 was the most complex one, which was difficult even for me, even though I wrote the system. But users were able to achieve this in around 50 minutes with a good performance, in general. All these users were mostly graduate students with 3 or 4 engineers as well, who were well versed with machine learning in general, but they had never seen TorchQL before, and they had to essentially learn it from scratch when they were giving this user study. So given all of that, we come to what we plan to do in the future with TorchQL. So as you saw over here, TorchQL is more of an evaluation framework where you get the predictions of a machine learning model and then you evaluate them or you constrain them. But we want to really get TorchQL into the training pipeline by essentially figuring out a way to effectively express differential versions of these integrity constraints and allow us to train models constrained by these integrity constraints. That's half of the battle is already done because TorchQL allows for end-to-end differential queries, but we still need to work on this. We also want to look at database optimizations in TorchQL and how we would be able to end-to-end synthesize TorchQL queries so we can hopefully give a NL natural language prompt and get the queries back. And so in conclusion, we're proposing a framework for programming and checking integrity constraints. And we showed that TorchQL is expressive, scalable, and interactive. And the code for TorchQL is available on our GitHub in case you want to try it out and give us feedback. And yeah, thanks for listening to the talk. I can address any questions now.
Go ahead.
Hey, Will from Brown. I'm curious about the performance comparison with Pandas. My understanding is Pandas is slower due to something about an inflexible schema, but can you elaborate on that? Like, what is TorchQL doing that permits it to be faster than Pandas while having a comparable API?
So, okay, so Pandas is not slower because of an inflexible schema. It's just that we cannot express certain queries in Pandas because of the inflexible schema. So over here, we were able to express every single query in Pandas. The reason Pandas is slower mostly comes from the joins that are required by these queries. So SQ1 and SQ2 are both join-heavy queries over here. So as we can see over here, they require joins over really large data sets. So it's so this is object detection. So this is the 15,000 frames that we saw in the example in the beginning. And that's where Pandas mainly suffers. It's in the join process when you have joins over a user-defined function. So for Pandas, you have to actually create new columns that run the function, get the outputs in those new columns, then join based on those columns. And that's where you get all the added overload. Added overhead.
Whereas how does TorchQL avoid doing that?
So TorchQL avoids actually creating new tables. Instead, it stores, it performs a hash join because all of the joins we are supporting are basically equivalent to SQL equijoins. So what we do is under the hood, we essentially store hash values for the outputs of each function and just map those hash values together. Instead of what Pandas does is it creates a new table every single time you need to actually create a join over a user-defined function.
Okay, thanks.
Other questions? Okay, I have one. I'm a big believer in domain-specific languages and how they can make things easier and make things work for a broader audience. So I'm curious about in your user study or maybe just in general the user group that you have in mind. Well, I guess to put it a little concretely, I noticed your operators are sort of database inspired, like join, right? So
Yeah.
how familiar were your subjects in your study with these terms already, or what do you expect from your end user groups? And is this something that you have to worry about more, or is this pretty good shape already?
So that is a good question. So the users in our group were mostly graduate students. And so we didn't really ask them we just said that you need some familiarity with databases, but we didn't really ask them like how familiar they were. But they weren't like hardcore database engineers. In general, I would expect most computer scientists to be familiar with this because this is mostly like SQL style operations, except maybe things like reduce and the fact that there are user-defined functions. But then again, we should probably conduct some more thorough, rigorous one from a more ML audience perspective, because at the end of the day, it will be machine learning engineers who are working on this and not graduate students mostly.
Okay,
Yeah.
thanks. We are right at time. Okay, thank you.
Right. Thank you.